Determine the flexure stresses at point A and point B in the cross section. Which one is the T cross section? We have given here the flange and the wave. Flange is of size 150 mm by 50 mm and the wave has a height equal to 150 by 50 mm. The bending moment at this section is M is given as positive value, that is because of sagging, and is equal to 20 kilonewton meter. So in this problem, first you have to calculate here the moment of inertia for a T section, as well as you have to locate the centroid position of this given T section. Now the given T section is consist of the standard two rectangle. One rectangle has a width equal to 150 and the height is equal to 50. Second rectangle has a width equal to 50 and the height is equal to 150. So we'll divide into two figure. We take a reference at the bottom here and we'll measure the individual centroid. The centroid will lie on this axis of symmetry. Only the vertical distance we have to calculate. So this bottom rectangle will labeled as 1 and its centroid will be exactly on this symmetry axis. Let mark here the centroid of the rectangle 1 is equal to C1, and from bottom this height is same as equal to 75. So we have Y1 is equal to 75 mm and the area of this figure is equal to 50 by 150. So we have Y1 is equal to 75 mm and the area A1 is equal to 150 multiplied by 50. Now this top rectangle will labeled as 2. First of all, we'll mark the centroid here. The centroid of the top rectangle is C2 and from bottom this distance is 150 plus 25. So the centroid is measured in a vertical direction and this value will be equal to Y2. This value of Y2 is 150 plus 50 divided by 2. That is equal to 175. So in this case we have Y2 will be equal to 175 mm and we have A2 is equal to same as equal to 150 by 50. 150 by 50. So for composite area we can locate our Y bar from the bottom and that value is given as A1 Y1 plus A2 Y2 divided by total area, which is the sum of A1 plus A2. So simply substitute all this value and solve for Y bar. In this case we have A1 equal to 150 and 150. It means that A1 A2 and this value will be get cancelled. A1 is same as A2. So in numerator we have Y1 plus Y2 and here in denominator we have 2 times of A. So divided by 2. That is equal to 75 plus 175 divided by 2. Total we have 250 divided by 2 will be equal to 125. That will be mm. So with reference to the bottom here, we'll mark the resultant centroid. Resultant centroid will be at a distance equal to 125. So it's towards the flange. So this one is the value of C. And this value of C is Y bar and we have Y bar is equal to 125. So this vertical distance is 125. Next we want to calculate the moment of inertia about the centroidal axis passing through resultant centroid G. For this one we have to use the parallel axis theorem. So for parallel axis theorem we have IZ. First we consider here the bottom rectangle, which one is IZ1 plus we have area A1 multiplied by perpendicular distance between C1 and the G, that is same as equal to the perpendicular distance between Y bar minus Y1 and we have to make a square of it, plus we have moment of inertia of the second figure, that is the top rectangle is IZ2 plus we have area A2 multiplied by Y bar minus Y2 and we have a square of this. So you have to solve this value of IZ. IZ for the bottom rectangle is 50 into 150 cube. So we have IZ will be equal to IZ1 is equal to 50. That is the base multiplied by height is 150. We have cube of it divided by 12 plus we have area A1 is same as 50 multiplied by height is equal to 150 multiplied by Y bar, which one is 125. Y1 value is equal to 75. So minus 75 square of it plus we have IZ2. IZ2 is BH cube. This Base is 150, height is equal to 50. So we have 150 into 50 cube divided by 12 plus we have area is equal to 150 by 50, 150 by 50 into we have y bar is 125 minus y2 value is equal to 175 and whole square. So solve this, you will get the value of Iz. So in this case you will get the moment of inertia is close to 53.125. That will be multiplied by 10 to the power 6 is mm to the power 4, and we have value of y bar is equal to 125 mm. So this data is required for further calculation. To calculate the bending stress at point A and point B, we have to measure the distance between the resultant centroid and point A. So we know the value of y bar, so we can very well measure the distance of the top fiber, that is at A, from the resultant centroid, as well as bottom fiber B from the resultant centroid. So I will use this data and I will go to the next slide. So one more time from the bottom I will mark here the distance y bar, which is equal to 125 mm. So correspondingly we can mark the position on axis of symmetry. So this one is the resultant value of G. So through the centroid we will set up our axis system. This is a standard procedure. Horizontal axis will be equal to Z, vertical axis will be equal to Y. Total distance from the bottom is 150 plus 50, that equal to 200. Centroid from the bottom is 125. It means that we have distance of YA. Since the point A is above the center of gravity, we'll take this value is equal to positive. Total distance is equal to 200, and the bottom distance up to the centroid will be equal to 125. So we have minus 125. So the distance of fiber A from the centroid is equal to 200 minus 125 is equal to 75 mm. Similarly, we have to calculate the distance of the bottom fiber at B from the center of gravity, but this point is below, so you have to treat the value of YB is a negative value because it is below the center of gravity. And at this point B here, the total distance here is same as equal to 125. So it's a negative minus 125 mm. Once we know the distance of YA and YB, and we know the value of m equal to 20, so we can calculate the flexure stress at A and the flexure stress at B. So we have a bending stress sigma B, which one is the function of y is same as equal to minus m into y divided by I. Bending moment is known, I is known. Depending upon the value of y, we have bending stress is positive or the bending stress is negative. As far as the point A is considered, y value is positive and this value of m is positive. So we have a bending stress at A will be negative. Value of m is equal to 20. So we have 20 into 10 to the power 6. Value of YA you have to use, that equal to 75, and is divided by IZ. IZ is same as equal to 53.125 into 10 to the power 6. Solve this, you will get negative value. Negative means compressive. So we will get this value equal to minus 21.18 megapascal. So on the top we have negative value, that is a compressive. Similarly, we can calculate the bending stress at point B. We have m value is same as equal to minus 20 into 10 to the power 6. So we have minus 20 into 10 to the power 6. Y value for bottom fiber is negative, is minus 125. Negative negative become positive. Divided by IZ is 53.125 into 10 to the power 6. So we'll get this value as a positive, and maximum value at the bottom come out to be 35.3. That will be megapascal. So as far as the A is considered, at A you have to show the negative value. So negative value I will show here, and this value is same as equal to minus 21.18 megapascal. Bending stress at the neutral axis will be equal to 0. So at NA it will be equal to 0. Then join the tip of the top bending stress, pass it to the neutral axis and extend it. So somewhere I will get this stress. So this one is a positive value of a bending stress. We have a straight line relationship, and maximum bending stress at bottom is 35.3 megapascal. So this one is called as the stress distribution in the case of T section. T section, we have a unsymmetrical distribution because the centroid is not exactly at the halfway, rather is offset towards the flange. So towards the flange we have smaller value, and to the wave we have maximum value. So this portion is called as wave, top portion is called as flange. So always in the case of the T section, we always get a maximum value of a bending stress at the bottom fiber of the wave. It can be tension or compression, it depends upon the value of M. If you have a sagging, then this value will be tension, and if it is a case of hogging, this value will be compression. But magnitude wise, at the bottom fiber of the wave, we always get the maximum possible value of the bending stress in the case of T section. A beam having a T-shaped cross-section is subjected to equal 12 kN bending moment, that is the value of M is shown. This value of M you have taken as a positive value because of a sagging. The cross-sectional dimension of the beam are as shown in the figure. We have T-section, flange has a width equal to 100 and the height is equal to 25. Wave has a height equal to 150 and the thickness equal to 25 mm. The centroid location is 110 mm measured upward from the bottom edge of the stem. So from this point we have the position of the centroid is 110 mm. So from the bottom stem we can mark the position of the centroid, that equal to G at a distance equal to 110 mm. And we have given the moment of inertia also, that equal to 18.464 10 to the power 6 mm to the power 4. Bending stress at a point A you have to find out, and you have to state the normal stress at A is tension or compression. You have to also find out the maximum bending stress produced in the cross section and state whether the stress is tension or compression. So we have given here the value of M, and the value of M is positive and is equal to 12 kilonewton. So M is 12 kilonewton meter. Then we have given the value of moment of inertia about the z-axis is given, that is the value of Iz is given, is 18.464 into 10 to the power 6. We have to calculate what is the bending stress at point A, and you have to also calculate what is the maximum value of a bending stress, and you have to state the nature here, whether this is tension or it is compression. Since we are interested to know the bending stress at point A, so we will set up our axis at G. Horizontal axis will be the Z axis, vertical axis will be the Y axis. So for point A, the vertical distance is positive, is 150 minus 110. So we have YA will be equal to 40, and you have to treat this value as a positive value. So the bending stress at point A will be same as equal to negative M multiplied by YA divided by I, that is value of Iz. Bending moment you have to take as Newton mm. So bending moment will be equal to minus, bending moment is positive value, is 12 into 10 to the power 6. Value of Y is also positive, and we have Y is equal to 40 divided by Iz value. This time Iz is directly given, is 18.464 into 10 to the power 6. So bending stress at point A will come out to be negative. It means that its compression and is minus 25.473 megapascal. That is, we have 25.473 megapascal but compression. Then we need to calculate the maximum value of a bending stress, that will be either at the top fiber or bottom fiber. So B represents here the top fiber, and for point B the vertical distance will be equal to 40 plus 25, that equal to 65. And if we consider the point C, which one is below the center of gravity, so you have to take the distance YC as a negative value, is minus 110. So we have YC equal to minus 110. Naturally here the bending stress is directly proportional to Y. So we have maximum value of a bending stress will be at point C. So we have sigma B maximum, and this value will take as a value of C. So we have sigma B maximum equal to minus M into YC divided by Iz. So we have minus m is equal to 12 into 10 to the power 6. Yc value is negative value is minus 110 divided by Iz is 18.464 into 10 to the power 6. So minus and minus become positive, so we are getting here positive answer is approximately equal to 70.8, that will be megapascal. And since the answer is positive, the nature of the stress is tension. So maximum stress in this case is 70.8. Already we have proved in the last problem that the bottom of the wave fiber will be always have a maximum value of a stress, maybe compression or tension, but depends upon the value of m. If it is a sagging, then we have a tension, and if it is a hogging, then it is a case of compression. It is a case of compression. So compression stress will produce in the case of hogging, tensile stress will produce at the bottom of the wave if we have a sagging. Two vertical forces are applied to a simply supported beam having a cross section as shown in figure. Again we have a T cross section. Flange has a width equal to 200 and depth is equal to 15 mm, and the wave has a width is equal to 9 mm and the depth is equal to 160 mm. This time we have simply supported beam given here ABCD. 2-point load is acting. One is 12 kN at a distance equal to 1 meter from A, and another 12 kN is acting at point C, 1 meter from the other support. We want to calculate here the maximum tension and the compression bending stress produced in the segment BC. So we are interested in the segment BC. So for this segment BC, we have to first find out what is the maximum possible bending moment. For that one, we have to find out the reaction at A and the reaction at D. Then you develop the shear force diagram and the bending moment diagram. Once we know the bending moment between B and C, then we can calculate the bending stress. That is the maximum value of the bending stress. The centroid location is 139.1 mm measure upward from the bottom edge of the stem. So from this point, the centroid is lying upward at 139.1, and we have given the moment of inertia 10.58 into 10 to the power 6. Now T section is symmetrical about this vertical line, so the centroid will lie on this vertical line at a distance equal to 139.1. So exactly this distance is 139.1, and we can locate the centroid on the symmetrical line. So axis of symmetry, we have centroid equal to G, and we have also given the moment of inertia Iz. So the maximum value of bending stress will occur either at top point A or bottom point B. For the top point, the distance you have to measure the positive distance, because at G will set up our axis system. Horizontal axis equal to Z axis and the vertical axis is Y axis. It means that we have Y is a positive value, and the total distance here Y will be equal to 160 plus 15 minus 139.1. So we have YA distance is the sum of 160 plus 15, that is the total length, minus we have 139.1, and this value of Y you have to take as a positive value is equal to 35.9, that will be mm, and the bottom fiber from the center of gravity is below. So this distance of YB you have to take as a negative value is same as 139.1. So in this case we have YB will be equal to negative 139.1 mm. Now to find out here the bending moment, first you have to find out the reaction at A and the reaction at D. Now this figure is symmetrical if I draw the vertical exactly at the midway between B and C. So this is a case of symmetrical loading. So reaction at A and the reaction at D is same as equal to 12 kilonewton each. So for symmetrical loading, we have RA is a vertical reaction at A and RD is a vertical reaction. So we have RA is same as equal to RD is same as equal to 12 kilonewton because of symmetrical loading. At point A, we have RA is equal to 12, so we'll move vertically upward by a load is equal to 12, so we have 12 kilonewton shear force. Between A and B, there is no loading acts, so shear force is remain constant. For 12 kilonewton, you have to move vertically downward. So this one is a one area that is formed, and this one is a positive value of a shear force equal to 12 kilonewton. Between B and C, there is no shear force. It means that it is a case of pure bending. At point C, you have to move vertically downward by 12 kilonewton. So this will be the minus 12, and from C to D there is no loading, so shear force is remain constant and reaction at D will be same as equal to 12. So we'll close at 0. This one is negative value of shear force. So this one is the shear force diagram. Now we'll construct here the bending moment diagram. To construct the bending moment diagram, we know the rule here that if we have a rectangle in shear force, then we'll get a triangle in the bending moment diagram. And if it is a positive, then you have to draw a line with a positive slope. So this one is a positive slope. That is, the area of the shear force diagram will be same as equal to the change in bending moment. So this distance is equal to 1 meter. It means that we have bending moment at this point will be equal to 12 into 1. That will be kilonewton meter. At B to C, there is no shear force acting, so bending moment is remain constant. So this one is a case of pure bending. And C to D, we have negative value and the area equal to minus 12 plus 12 at minus 12. So we have 0 value at D. For the section BC, the bending moment is constant and is equal to 12 kilonewton meter. We know that the bending stress sigma B at any distance y is given as minus of m multiplied by y divided by iz, and iz is given to us, and for A we have y is also known, that is 35.9, and for this case it's a positive value. So for sigma B, that is the bending stress at the top point, that is A, will be equal to minus m is 12 kilonewton meter is 12 into 10 to the power 6. Y is positive value is 35.9 divided by iz is 10.58 into 10 to the power 6, and this is coming out to be negative value, is approximately equal to minus 40.7 megapascal. It means that bending stress at A is compressive in nature and is equal to 40.7 megapascal, but compressive in nature. Using the same formula, we can calculate the bending stress at point B will be equal to minus m, and we have m is equal to 12 into 10 to the power 6 multiplied by yb distance is negative 139.1, and whole thing is divided by iz is 10.58 into 10 to the power 6. Negative and negative, it become positive value, and approximately this answer is close to 157.8, that will be megapascal. Positive value means that we have a tension. So bending stress at point B, that is the bottom fiber, is 157.8 megapascal and tension. So continuously we have done the 3 problem in the T section, and for every problem at the bottom we are getting the maximum value of a bending stress. So this one is maximum value of a bending stress, and on the top fiber we have compression is equal to 40.7 megapascal. The video you are watching is from the app, which is the Mode Class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.